Welcome to lecture number 2 of your physical meteorology course. I'm wearing the same thing that I wore lecture number 1. We won't go into that, but anyway, let's pick up with right where we left off, expanded discussion of the forces. So this is a continuation of topic number 2 within lecture number 2, dealing with how these, eventually I'm going to show how this all applies to forecast models and so on. So this, as I said, picking up where we left off in lecture number 2. Let's actually move into the actual forces in the atmosphere. In the previous lecture, I left off talking about the forecast equations, where we're taking the U component and the V component of the wind with respect to time, and we're forecasting that out in time. And to do that, we then take into account our starting time, our net forces, our mass, and our ending time, or our forecast time. We need to talk about this net force that we're throwing in there. So let's go into our discussion about the different forces in the atmosphere. To solve for the equations of motion for horizontal winds in the Eulerian framework, we need to take into account the net force per unit mass. So this net of forces that we're talking about. Remember in this equation here, this F sub net that we were throwing in there. Well, this equation itself, there's a lot going on. But just wait till you see what's going on right here. So what is this net force that we're referring to? Well, we have several different forces that we have to take into account. One being advection. Advection in these different equations will be represented by AD. We also have the pressure gradient force, which will be represented by a PG. The Coriolis force, represented by a CF. Turbulent drag, represented by TD, and centrifugal force, represented by CN. So these are our different forces that are all examined or taken into account with our net forces. Now, this is one thing to know that all of these are contained in there. It's another thing to know, okay, what is contained within the advection force. As I said, a variable within just one of these can affect this, which affects this, the end result. So it's important for us to understand, or for you to understand, all of these different aspects. Let's talk about our first one, the advection force, or advection, in this particular case. Winds can blow air having a different temperature and humidity into a region. So that's why advection is important, and that's what advection is, the movement of air advecting into another area. So one air mass advecting into another type of air mass. So differences in temperature and moisture content moving into a region. Winds can also blow air with a different momentum into a region. Now this is important because remember, our parcels of air will move with respect to their mass. Something heavier is not going to move as fast as something that's not as heavy, or something that does not contain as much mass. So we need to take into account that things are going to move differently. So something that's moving quickly here may not move as quick over here. So an air parcel in this environment may move very fast. An air parcel over in this environment, that same air parcel, may move slower. So we have to also take into account those aspects. This is your advection equation. Now you can see, remember, it was all nice and neat in that first equation dealing with force sub net, or your net forces. Now when you're looking at, oh Lord, this goes into there, well there's a whole bunch of these long equations that are going into those net forces. This is what we're trying to solve for. F of x AD, or our force of advection. Or our force of advection, we have to take into account mass. How do we determine our net force of advection? Well, we have to take into account the U component to the wind. The U component to the wind is your west to east wind. So our respect to our U component wind and also our V component wind. Well, this is simple. All we're saying is advection, we solve for advection by taking into account the movement of wind from west to east and the movement of wind from north to south. We also have to take into account the mass of what we're moving, and then we're able to find the force of the advection. So even though, let's just take moisture advecting in from the Gulf of Mexico. Moisture may advect north from the Gulf of Mexico into the southeastern United States. Well, even though it's a movement in the in the south to north direction, we also have to take into account that there may be some movement of air from west to east. This movement of air from west to east, because that could cause the wind to veer. That could cause the wind to slow. It would have an effect. So anytime we're dealing with these forces, we have to take into account forces in all the directions. So that's why you're going to see that there are actually two equations. The second equation, same exact equation, we're just taking into account wind in a different direction. We're taking into account the wind in the y aspect here, or the wind in the south to north direction. Our second force is the pressure gradient force. Pressure gradient force always acts perpendicular to the isobars, or height contours on a weather chart. So if your pressure bar, your isobars are running elongated like this, the force will not act with the flow, the force acts across the flow, so to speak. So that's what the perpendicular means. This force is present regardless of wind speed. So there may not be any wind, but there's always a pressure gradient force. The pressure's not the same everywhere. This is our pressure gradient force equation. And again, there are two of them. We have to take into account a change in pressure from west to east, as well as the change in pressure from north to south. To calculate the pressure gradient force, we have to take into account the mass of the air parcel once again. So this air parcel that may move as the result of the pressure gradient force has some mass. We determine that force by taking into account the pressure and the density. So the pressure and the density and our air parcel moving in the east to west direction, or west to east direction, and also our north to south or south to north direction. So those are just the variables that take into account the pressure gradient force. Pressure gradient force can be impacted by pressure and density. What affects density? Density can be affected by temperature, moisture content. That can have a direct impact on mass. That can have a direct impact on the pressure. So you can see that one small variable can affect another variable, which can affect the variable, which can affect the force. This force then can affect the end result, net force. That net force can affect the end result of the wind velocity. The pressure gradient force is the only force that can drive the horizontal winds. Coriolis, drag, centrifugal, and even advection all disappear for zero wind speed. So in other words, if we do not have a wind speed or we do not have wind, the others disappear. So pressure gradient force is always present. Our third is the centrifugal force. Newton's laws of motion state that an object tends to move in a straight line unless acted upon by a force, and that's basic physics. Centrifugal force assumes or causes air parcels to pull outward from the center of a turn. So this causes air parcels to pull outward from the center of a turn. These are our equations for centrifugal force. Again, there's two of them. We'll just look at one here. We're taking into account the force. That's what we're trying to find. Of course, we have to have that mass of that air parcel that we're moving. We determine that by taking into account velocity. So this is our velocity with respect to r here. Now what is r? Actually, I should go back here. Forget to say that there's an s in here. S is a constant. So with those particular equations, there's three variables. Velocity. These symbols here represent absolute value. So velocity, r, and this little s to determine the centrifugal force. The little s is the sign coefficient, a provided number based on the situation, and r is the radius of the curvature. When we're dealing with troughs and ridges on a weather chart, there's curvature to the flow. So we have to take into account that curvature. We also have to take into account the actual situation. The situation being if we're dealing with low pressure or high pressure, a trough or a ridge, and also if we're in the northern hemisphere or the southern hemisphere. So if you're plugging numbers into that particular equation, these are the numbers that would be assigned given the situation. Low pressure, high pressure, northern hemisphere, southern hemisphere. Number 4 is the Coriolis force. And of course you've heard this many, many times in the courses you've had thus far. The Coriolis force is defined as that. Coriolis force is represented by the F sub c for Coriolis force. 2 times your omega symbol times the sine of omega. That's the actual equation for the Coriolis force, where 2 times omega is equal to some given value. And actually I said that was omega there. That's our other symbol going on there. That represents the latitude that we're at. And then finally, here's our actual Coriolis number. The reason I'm giving you that is because we're holding it constant at middle latitudes. So what does that all mean? This is just a bunch of fancy numbers and equations and symbols for me to show you. But what I'm also telling you is we're going to basically in the mid-latitudes, which is where you're primarily forecasting the weather for, Coriolis force is usually a constant. The Coriolis force acts perpendicular to the wind direction. It will turn things to the right in the northern hemisphere and to the left in the southern hemisphere. So basically what we're saying, relating back to Newton's law, that the air would flow in a straight direction. However, we're dealing with the curved surface of the earth and also the Coriolis force created by the rotation of the earth. So because of that, things do not travel in a straight line. Our air parcels will not travel in a straight line. For the northern hemisphere, the Coriolis equation, well, those were all out of order, is as follows. So ignore all that other stuff. That's just how Coriolis force is found or determined. Just giving you some background information. These are the actual equations that go into that net force that we started with. Again, there's 2, one for east to west, one for north to south. To determine our Coriolis force, we have to take into account the mass of that air parcel we're trying to move. There's the actual Coriolis value that's given plus the velocity. So how fast is the air moving? That's going to determine the Coriolis force. If there's no wind, there's no Coriolis force. Our 5th is turbulent drag. Turbulent drag. What is that? Air experiences a drag on the Earth's surface. Drag will slow the wind. This drag changes from one particular type of terrain to another. If we have a open field versus a highly urbanized area, downtown area versus a wooded area, we'll have different types of drag. And there's actual values that you can assign based on the type of drag and the type of terrain that you're dealing with. So the wind obviously will be slowed or allowed to flow faster given different situations. This drag only occurs within the planetary boundary layer. We haven't talked about the planetary boundary layer yet. We'll get into a lot more detail with it in the actual next section. But know that this is occurring down near the surface in that lowest 2 kilometers near the Earth, near the surface of the Earth. This is important because we can forecast the weather down here in the planetary boundary layer. Forecast the winds over different terrains, water, flat grasslands, forests, cities, etc. So we need to take into account this drag, particularly when we're dealing with forecasts for wind down near the surface. The drag force acting on the planetary boundary layer is represented as follows. So we have two types of equations here. Again, one for our U component, x direction, one for our V component, y direction. Dealing with the force, turbulent drag force, we have to take into account that mass once again. We have this W value in here, and then of course the wind, and then the layer, or represented by Z. So here's all of our givens. Where Z is the depth of the planetary boundary layer, we need to know what type of a depth are we dealing with. The W sub T is the transport velocity. Oops. The transport velocity. This basically takes into account the drag. What type of terrain are we dealing with? So this value will change depending upon the type of terrain. Forecast models take this stuff into account, dealing with the different areas of the United States. So primarily three different variables. The velocity of the wind, or your wind component, the depth that we're dealing with, and the amount of drag that's taking place within that layer. During windy conditions and near neutral static stability, what we're basically saying is the atmosphere is not stable, it's not unstable. Turbulence will be generated primarily by wind shear, a change in wind direction with height. So anytime we're dealing with turbulence, we're changing the wind direction with height. For example, you have a southerly flow down near the surface, winds become more west or northwest as you move aloft. Sometimes these changes in directions can be subtle, sometimes they can be very abrupt. The more abrupt changes in wind direction with height usually occur near frontal boundaries, or after a frontal boundary moves through. So during windy conditions and near neutral static stability, in other words, we cannot have rising air parcels. So it cannot be unstable. Turbulence is generated primarily by wind shear, changing of wind direction with height. The turbulence is generated at the planetary boundary layer. This turbulence is then transported upward. So don't just think of this as dealing with turbulence that's occurring down near the surface and it's going to affect wind speeds down near the surface. You have to understand that in neutral static stability, that turbulence that is generated down in the planetary boundary layer can be transported upward. And when it's transported upward, it can affect things happening at the 500 millibar level, maybe the 300 millibar level. So you've got to think outside the box, so to speak. Understand that just when I'm talking about all these equations, one little change in a variable can change things way out at the end, or your end result. Something happening down near the ground can have a direct impact on something that's happening in the mid-levels or aloft. So it's important to understand that the turbulence down near the surface can be transported upward. During light winds and unstable conditions, strong daytime surface heating will result in buoyant thermals transporting some friction upward. So when the winds are light, but conditions are unstable, particularly a typical summertime afternoon, you're not dealing with, you usually don't deal with that windy type of conditions, particularly when you get away from the northern, more latitudes, you move towards more of the southern United States. Here in Mississippi during the summer, there's not much wind. Really don't get those strong cold fronts moving through the area that you may see in the upper Midwest or in the Northeast. Well, during the afternoon, winds are light, things become unstable. You'll get these big bubbles of air that will become buoyant and move upward in the vertical. When that happens, any friction that's being created down near the ground can actually be transported upward. And that friction, or the effects of that friction, can actually have impacts on things happening aloft. This brings us to the full equations of motion. So it was all nice and neat with that, the first equation there, dealing with the net forces. Now we're going to combine all of this to produce our full equations of motion. So we're going to take into account advection, the pressure gradient force, the Coriolis force, and turbulent drag. We're going to put all of those together so you can see all of the variables in each one of those and how they all combine to give us our end result. And this will produce what is known as the full equations of motion for the atmosphere. Notice I left one out, and that was centrifugal force. Centrifugal force is excluded because it's an imbalance of all the forces, and that imbalance is already included. So we just toss that one out. It's taken into consideration already. The full equations of motion are written as follows. And again, there are two of them. One for your U component, one for your V component. Now, remember, all of this stuff before was represented by F net, or your net forces. I can expand that out and show you everything visually. So now you see all of the components that are coming into a play to give us our end result. So what is everything you see here? What's going on here? This first variable right here, this is tendency. So we are finding tendency, provides the change in wind direction through time. This is what we're trying to find right here. This is our advection part, this section right here. This is the advection component. The advection component here provides the amount of new air advecting into the region. So what type of new air is advecting into the region? Now you can see that all the variables that are being taken into play, the change in wind direction in our different aspects, north to south, east to west. This is the pressure gradient portion of the equations. And again, we're taking into account pressure and density. So this is the pressure gradient part. This little part right here is your Coriolis factor that's taken into play. And then finally you have your turbulent drag. That's the end component here. Now obviously if I would have showed you all of this stuff at the beginning, you would just be overwhelmed. But we took each one of these and broke it up and gave you the basic concept behind it and what's going on. So what I want you to do is understand all of the variables that come into play. So if one particular model's resolution for the end result in the wind is different from another computer model's resolution, you need to know that, okay, something's going on way back in here. Something's different between those forecast models. We need to consider some physical processes that are neglected in these equations. So there's those long equations right there. There's some things that are neglected that you have to take into consideration, because they vary from one situation to another. One is molecular friction. This is significant at the bottom few millimeters of the ground. So this is something that, it's a variable that's thrown in. We're not going to go into the equations and all of that, but understand that down near right near the surface of the ground, we have to take into account the effects of the wind. In mountain areas, we have to take into account mountain wave drag, and this occurs in mountainous regions. The wind will be impacted as it moves through a mountainous area. So this is sort of representative of terrain. I've already talked about terrain. So this is an effect of drag, but we have to take that effect of turbulent drag a little further when we're dealing with mountains. Convective mixing occurs above the planetary boundary layer from turbulence produced by cumulus clouds. So when we're dealing with an environment where we have a lot of cumulus clouds, these clouds actually create turbulence themselves, and that turbulence can have an impact on the general wind pattern. Mean vertical motions, large-scale subsidence has been neglected thus far. This is considered later on. The winds themselves, when you deal with a lot of subsidence, that can actually slow the winds and cause some impacts on the winds there. So we have to take into account some synoptic scale features. All right, we'll leave the equations of motion. And let's go into some different topics here. And again, a lot of this was covered in synoptic meteorology. We're just taking it a little step farther, going in a little more in depth. The full equations of motion are given using Cartesian coordinates, x, y, and z. Z is the geometric distance above ground level. Z is referred to as our vertical coordinates, so to speak. An alternative coordinate system can be used, pressure, as a vertical coordinate. So in meteorology, we talk about pressure. We don't refer to 10,000 feet, 20,000 feet. We refer to 850 millibar level, 500 millibar level, etc. So the pressure coordinates then are rewritten as x, y, and p. So just understand that z component is altered sometimes in meteorology and turned into a p. They're both representing that vertical coordinate, however. An isobaric surface is defined as, and again this is a recap, as a surface indicated on a chart, surface meaning a horizontal slice across the atmosphere, so 850 millibar level, 700, 500, connecting points of equal pressure. Once we leave the actual ground level, where an area of low pressure or high pressure is just that, we're dealing with areas of low and high heights. That's important. If you ever want to impress somebody in meteorology, when you're talking about a surface chart, you can say high pressure and low pressure. But when you go up and look at an 850 millibar chart or a 500 millibar chart, you see an H or an L on there, you're not really looking at high pressure and low pressure. You're looking at high heights and low heights. So if you want to talk the talk, so to speak, and actually be technically correct, if you're looking at an 850 millibar or 500 millibar chart or whatever level up there, you're looking at high heights or an area of low heights. Don't refer to it as, well, there's a big high pressure at 500 millibars. Don't say that. The pressure is 500 millibars. That's the level you're at. You're at the 500 millibar level. That's the pressure level. If you see an H and an L, that's high heights and lower heights. The higher heights representing warmer temperatures, the lower heights representing colder temperatures. So that's the proper way to talk about it. So once we leave the actual ground level, you're dealing with heights. This is what's indicated on the upper level weather charts, as I said. The hydrostatic equation can be used to convert the pressure gradient terms from height to pressure coordinates. So here's our east to west component and our north to south component. So this is a force for the pressure gradient. We can also rewrite it in this form, where a change in z with respect to a change in x here. And we're taking into account gravity. So this is the hydrostatic equation. We already saw this in calculus form, or something very similar. This is just rewriting it in algebraic form, where the change in z divided by change in x and change in z divided by change in y are the slopes of the isobaric surfaces. Example, the change in height with distance. So that's what we're taking. That's anytime you see something like this, the change in height with distance. Understand that it is taking into account the forces created by that. Taking into account, we have to include the mass, the gravity, and our changes in height. Geostrophic wind. Again, cover this in synoptic meteorology. Just going to recap it here. Geostrophic wind, represented by UG and VG. Again, there's two of everything in meteorology. We have to look at it in both directions. Is a theoretical wind that results from a steady state balance between pressure gradient forces and the Coriolis force. So it's a steady state balance. Those are our two equations. What's taken into account here? Well, we're looking at pressure, we're looking at the Coriolis force, and we're looking at density. All of those variables will determine the geostrophic wind. And the same thing, we would do the same thing to look at the wind in the south to north component as compared to the west to east component. So why am I showing you this? I'm showing you this to tell you that the geostrophic wind takes into account pressure, Coriolis force, and density. Anytime you hear the flow is geostrophic, the flow is geostrophic because of these variables. So these variables are coming into play to produce the geostrophic wind. This equation determines the geostrophic wind speed at the surface based on a change in pressure across some horizontal distance. So the change in pressure across some horizontal distance. In regions with straight isobars above the top of the planetary boundary layer and away from the equator, the actual winds are approximately geostrophic. So what we're saying there is, once you leave the surface, the wind will usually be geostrophic. Here's another set of equations here. There's taking into account the same thing, but we're looking at geostrophic wind. The same variables, gravity, Coriolis force, just set up a little differently here. The plus and the minus shows up in there primarily because we're changing direction from north to south or east to west. G is the gravitational acceleration. That's a given, 9.8 meters per second squared, and Coriolis force. This equation determines the geostrophic wind speed above the surface based on a change in horizontal distance between height contours on a constant pressure chart. And again, just recapping some things from basic meteorology. So your geostrophic wind will flow with things, or with the general height lines. Your gradient wind. Gradient wind defined: the curved steady state wind around high and low pressure follows the curved isobars. Around low pressure, the wind will tend to be slower. This is called subgeostrophic. Around high pressure, the wind will tend to be faster. This is called supergeostrophic. The gradient wind occurs because of an imbalance between the pressure gradient and the Coriolis forces attempting to balance the centrifugal force. A lot of forces coming into play here, and they're all trying to balance everything out. Something you probably learned in basic meteorology is weather occurs because Mother Nature, the atmosphere, whatever you want to refer to it as, is trying to reach equilibrium. It's an attempt to reach equilibrium. And in that attempt to reach equilibrium, we create things like storms, frontal boundaries, and so on. The gradient wind occurs because of this attempt to balance all of these different forces that are coming into play. The gradient wind is represented by M sub r for cyclonic flow around low pressure. And this would be the equation. This is a scary looking equation here, but this is the equation for gradient wind. So I'm determining gradient wind. It's actually not that bad. There's some variables that are coming into play. You already know this one, the Coriolis force. R probably is the radius. You know, you're thinking it's probably radius. I saw that already. Then you have G over here, Coriolis, and radius again. G is your geostrophic wind. The gradient wind for anticyclonic flow around high pressure is given as follows. And so there's two different equations for one, cyclonic flow and anticyclonic flow. And here's your variables in both of those. G is your geostrophic wind. R is your distance or radius of curvature. And F sub C is your Coriolis force. So those are your primary variables that are coming into play to determine the geostrophic wind. Again, why am I showing you this? I'm just showing you this so you understand the different variables that come into play to determine these things. When you pull up a weather chart and you see it's showing the wind flow, it's isobars, isobaric surface, whatever you're looking at, height lines, understand it came from it's coming from somewhere. And there's some variables that are coming into play to produce these weather charts that a lot of people take for granted. The curvature is referred to as a Rossby number. This is the radius of curvature. So that R is your Rossby number. Here's a weather chart. Said we wouldn't look at weather charts. Well, I'm surprised you. Here's an actual weather chart. I don't know what level this is. We're not at the surface. We're dealing... I wish I would have remembered what surface this was. Oh well. But we're dealing with, we're showing some some height lines on here, and we also have some plotted wind barbs. Let's focus on one particular area. Let's come up here to the Pacific Northwest. So let's zoom in on that. It's a little easier to see. This is gradient wind. And the reason it's a gradient wind is because we're dealing with curvature. There's a curvature to the flow in here. You should be able to see that easily. Over here, there's no curvature present, but back in here there is a curvature to the wind. All right, if that's the actual curvature, let's look at the observed wind barbs. Look at the observed wind barbs. In this particular case, the wind barbs are not running with the flow. Some of them do. Some of them are they're slightly off, and they're slightly off due to the curvature. So this is referred to as gradient wind. Let's take that same weather chart. Let's focus on a different part of the United States. Let's zoom in here. We'll call it the Midwest, the Mid-South. Here things are a little bit different. We don't see a curvature. The height lines are perfectly straight. The flow is pretty much southwest to northeast. This is a geostrophic wind flow due to the lack of curvature. Note that the wind barbs are pretty much all running straight with your height lines. Now, this one starts to sway, and you can sort of see a curved line down here. There's actually some curvature to the flow down here off the screen, and that's actually having an impact on the winds here. So you can see how over here the flow would be more gradient. Here it's more geostrophic. Generally speaking, your flow will become geostrophic as you move aloft. We also have to take into account the boundary layer wind. We have this wind that occurs down near the planetary boundary layer. Boundary layer wind is represented by M. I should have pointed out wind in this particular case is represented by a capital M, and then sub BL represents boundary layer. So in his other previous examples, the capital M is representing the wind. Turbulent drag in the boundary layer slows the wind below the geostrophic value and turns the wind to a point at a small angle across the isobars. So, in that particular case, you need to understand that the boundary layer wind, that's the wind down here where we are, that's where you're forecasting for, that wind is going to have a slight curve to it. So the turbulent drag down in the boundary layer is going to affect that wind and cause it to turn and actually cross over the isobars. The pressure gradient force, Coriolis force, and turbulent drag are all considered to determine the boundary layer wind. So we have to take into account all of that. Here's an example. Here's an example of boundary layer wind. This line right here is representing 99 kilopascals, 100 kilopascals, 101 kilopascals. So lower pressure on this side, higher pressure over here. Our gradient wind, or geostrophic wind, or whatever we're dealing with here, our wind flow typically would be with these contour lines. However, the boundary layer wind is going to curve slightly in toward the lower pressure. Lower pressure, the wind will pull in towards the lower pressure, so it's going to curve to the left in this particular case. So, when you're looking at isobars on a surface chart, the wind will not always be flowing with those particular isobars. Understand that the actual wind may actually turn and cross the isobars, and in this particular case, toward the lower pressure. We also have our boundary layer gradient wind. Our boundary layer gradient wind, what is that? This occurs in regions of curved isobars at the bottom of cyclones and anticyclones. So when we're dealing with a curve flow, we're dealing with a gradient wind in the boundary layer. In addition to the pressure gradient force and Coriolis force, drag is present in the boundary layer, so we have to take into consideration that. Air will tend to spiral in toward low pressure, and air will spiral out from high pressure. And then finally, we have something that you've probably never heard of before, the cyclostrophic wind. And some may have heard of this, but this I found was a new term. I actually learned a little bit about this when I was doing the research for the course. Cyclostrophic wind. With intense vortices, strong winds will rotate around a very tight circle. Now this is intense vortices. These intense vortices, what are some examples? Well, tornadoes, waterspouts, hurricane eye wall. These are all referred to as intense vortices. They're a smaller scale. We're not dealing with high pressure or low pressure, or these large mid-latitude cyclones. When we're dealing with that, we can determine the wind, based on a certain set of variables. When we bring things down, however, we have to take into account some different aspects. And one being, we're dealing with something on a very small scale. So the cyclostrophic wind, tornadoes, waterspouts, hurricane eye walls, something at a very small scale. Centrifugal force and pressure gradient force dominate in all of these aspects. So in all of the aspects, pressure gradient force and centrifugal force dominate. Coriolis force and surface drag are very small, so we throw those out. Centrifugal force and pressure gradient force. If you think about it, a hurricane has an eye wall. Within that eye wall, you have a very tight pressure gradient. We're also dealing with the spin, or the round cylindrical form to the system. Those dominate. Any effect from Coriolis force is going to be canceled out by that. Any effect by drag will be canceled out. Now, drag itself and turbulence on the surface of the Earth can actually have an impact, especially when you're dealing with a tropical system, and actually tornadoes and waterspouts and so on. So that will have an impact, but actually calculating the wind, we don't need those variables to calculate the wind. Given these circulations are often associated with a larger scale circulation, such as a high pressure, we solve the equations in cylindrical form as follows. And there's the equation for your cyclostrophic wind. Now what I mean by they're usually associated with some parent circulation. You have a low pressure, an area of low pressure with its attending cold front. Well, there's a circulation associated with that. Now we bring it down a scale. We have a thunderstorm that's being caused by that parent circulation or parent system. The thunderstorm itself develops a rotation, a mesocyclone. That rotation spins up a tornado. That tornado itself has a rotation. So there's a curvature to the tornado, probably to the rotation in a thunderstorm, and a curvature to the storm system that's causing all of that to happen. So we have to take into account, everything's linked. So keep that in mind. Go back to the equation here and look at all the different variables that come into play. Cyclostrophic wind is equivalent to our tangential wind. And this is a geometry form here. To solve this, we take into account R, rho or density, a change in pressure, and a change in R. So all our different variables are R is the radial distance outward from the center rotation. Delta P over delta R is your local radius pressure or radial pressure gradient. And M sub tan or M tangent is our tangential wind speed around the vortex, which is the cyclostrophic wind. So take into account all of that. And as I said, it is driven by the pressure gradient and also that radius of the system. Now, of course, we have to also take into account density. So that's something new. And that becomes important when we talk about hurricanes and so on. And that basically brings us to the end of topic number 2. So, cyclostrophic wind is picking up on that. We'll bring that back in more detail when we talk about tropical systems because, as I said, it's an example of where we would use that to determine wind speeds, determining wind speeds in an eye wall. So in summary, what I'll do is the beginning of the next lecture, lecture number 3, I will actually bring some weather charts in, some actual computer forecast models, and we'll examine those and look at the different forces and so on, just to sort of recap everything that we just talked about. And then we'll move on to our next topic, which would be the planetary boundary layer. So in short, from this entire lecture on forces and so on, sort of taking things that you learned in synoptic meteorology, the whole point of this lecture is to get across to you that the calculated wind speeds, or whatever we're calculating, that's generated or outputted from a computer forecast model that you look at on a chart or on a computer screen, that is impacted by many different variables, many different net forces that you have to consider. And you need to know that all of this leads to that end result. So that concludes topic number 2, as well as lecture number 2 for your physical meteorology course. I'll see you in lecture number 3.